All right, so I am going to start today just by kind of going through and going over just some of the details about the exam itself. So, your final exam on Wednesday is a cumulative exam, meaning it covers everything that we did throughout the entire semester, going all the way back to chapter one, going all the way through Palmer's chapter 14. It will be Wednesday at 8 o'clock. It will be in this room. Now, I will warn you, this room has a divider in it. Chances are pretty good that the divider will be taken out and that the seat will probably be certain, but if history dictates anything, the seat probably all facing that direction. So when you come in, don't be surprised if they don't have to go through just because that's how this room basically doubles as a large lecture testing facility, so that courses like Math 102, which have maybe a couple hundred students in it, can have all testing all at the same time, credit project. So that's what's going to be going on in here. Now, as far as the exam itself is concerned, you can see here the breakdown. 88 questions in total. 68 of them are multiple choice. 12 of them are matching. There is a short answer section as well. So with 80 questions at the beginning, I will be giving you a scan sheet for them, and you'll report all of your answers on that bubble sheet. The remainder, the 8 short answer questions, which does include a bonus question, that will be something you'll have to actually write on the page of the test itself. Total value of the exam is 150 points. And like I said, there is bonus rolled into there. If we do kind of the math on this, this means that this exam is a little bit less than 2 of the other exams that you took this semester. So the final exam does not get its own portion of the grade. It is rolled into all the other exams. So if you've done well on the other exams, it means that you don't have to do as well on this one to kind of make up for it. So, as far as resources are concerned, basically the same rules as all the other exams have been. You're allowed the periodic table that I gave you in chapter 4, with all of its markings and notations on it. You're allowed those 3 exam pages from exam 1, exam 2, and exam 3, and you're allowed to make a 4th page just for the final exam. When you turn in your exam, you will turn in all of those materials with your exam as you complete it. Now, as far as the breakdown of questions are concerned, I didn't do a formal breakdown of how many questions from each topic and that kind of thing. It is a relatively even spread, though. The only chapter that might have slightly more with it is there might be a couple of extra Palmer questions on there just because you did have an exam over Palmer. Best places, things to do to study. Again, you've got access to all of your food and your homework. You can go through that material again. You have all of your graded exams. You can go through those again. There is a good chance that some of the material on the final is going to be constructed of questions either the same as or similar to questions that you saw on those hourly exams. So going back and doing those kinds of problems that you've already done before are going to be probably the best use of your time as far as studying are concerned. All right, any questions about the nature of the final exam itself before I take some of your own questions about just topics and material? All right, so I have here the practice test that I asked you to go through. Are there any questions? Is there anything specific that you wanted to kind of go through to prep for this exam? Tristan. Okay. 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 So recognition of the different types of radiation largely comes down to definitions. You have to know what the definition of an alpha particle, a beta particle, and a gamma ray are. And if you can do those things, then yes, it goes a long way toward helping. So let's see if we can find, I know there is a transportation question on here. All right, so right off the bat here, if you know your lowercase Greek letters, that's one way to go about determining alpha, beta, and gamma. The fish symbol here, that is the Greek letter alpha. The kind of elongated B here, that's beta. The curly Q here, that's gamma. So if you recognize those three letters, that's part of it. So right away you can recognize these first two as beta decays just by looking at that Greek alphabet. So that's one way to go about it. The other way to go about it is looking at things from the standpoint of solving these equations. And so what you have to remember is that transmutation reactions are not worried about conservation of atoms, they're worried about conservation of particles. And so what we need to look for are conservation of the mass number on top and the atomic number on the bottom. That's how we can keep track and make sure that everything that we started with, we end with. And so if I look at tin, SN here, I see that I have a mass number of 119. Now, since the beta particle is basically an electron, has virtually no mass but a -1 charge, just like an electron does. Since it has basically no mass, the thing that we're looking for here is going to have all of the mass that the tin had, 119. Because none of it went into that other particle. The other part comes from, now we got to get the periodic table involved. I look to the periodic table, I see that tin, SN, is element number 50. Its atomic number is 50. So there are 50 positive particles, a total charge of positive 50 on the left-hand side of that equation. Now the beta particle has a charge, but it's -1. So how many positive charges do I need to get 50? Well, it's just 51. If I have 51 positives and 1 negative, one of those positives and one of those negatives will cancel out. And I'll have 50 unneutralized positive particles left over. So the answer here is 51. 51 plus the -1 gives me the 50. So now I need to look at the periodic table again. What element has an atomic number of 51? SB, antimony. And that's all we have to do. So in problems like these, where we're trying to find the missing nucleus, basically, we can look at what we had at the beginning, what got pushed out of that nucleus through the process, and figure out what is left over once that process took place. Now we can recognize this beta decay because of the nature of the beta particle itself, either by the Greek definition or by recognizing the particles themselves for what they are. So a beta decay has no mass but a -1 charge. It's basically an electron. Alpha decay, we have a substantial particle that's being ejected. And so we can either write this as 4,2 alpha, or less commonly, but still correct, 4,2 helium, because helium is element number 2. It has an atomic mass of 4 and an atomic number of 2. So we can call it helium as well. Now, so remember, these are radioactive. They're unstable. The stuff that is on the periodic table is largely stable isotopes. Remember, the periodic table gives you the weighted average of the known isotopes of that substance. And the stable isotopes are going to be far more common than the unstable ones. And so that number is going to be reflected in there. Usually when we see a number on the periodic table as far as atomic mass, it's going to represent a stable isotope of that substance, not an unstable one. And if it's stable, it doesn't go through these kinds of decay. Because the whole point of this decay is to stabilize the nucleus as a result. So if you look at tin, you're right, tin 119, yeah, that's pretty close to its atomic number. If it went through that way to get to antimony, yeah, the antimony would be a little bit less stable than we would expect. But usually what we see is something more along the lines of like the second one here, where we've got technetium 87. And if we look at the periodic table, technetium should be somewhere around 98. Big gap between where we are presently and what expectation would be. And as a result, not surprising at all that it undergoes a beta decay or any kind of decay to try to get more stable. So again, if we look at the second one, technetium undergoing beta decay, what would be the mass number for our missing particle? top one, be 87. Again, beta particle has no mass, so the mass number would not change. Now, technetium is element number 43. So if it underwent beta decay, what would be the atomic number, the bottom number of this new nucleus? It would be 44. Same line of reasoning. Beta particle gives us an extra negative charge, so we need an extra positive charge to counteract it. Element number 44 is ruthenium, Ru. So that would be the balanced nuclear equation. Okay, so that's how we do the first two. Now for the last two, we're given the particle, we're given the new nucleus. We need to figure out what the particle that was ejected was, and therefore what the type of decay is. So here I have radon 222 converting to polonium 218. I look at radon, radon's element number 86, and polonium's element number 84. I have to ask myself the question, with that information, what's missing? All right, so yes, we're starting with a mass number of 4 because we've got 4 missing from the left side to the right. Now on the bottom, how much is missing? It's just 2. So in this case, again, there are 2 possible answers. Since we have an atomic number, we can go to the periodic table. Atomic number 2 is helium, He. This would be a correct answer. Now, if we go back to what we were looking at before, under our definitions, we would have to recognize that alpha is this as well. So 4,2 alpha would also be a possible answer. That would mean that this type of decay is an alpha decay. Right, now, this last one's kind of tricky. We're dealing with phosphorus. Phosphorus atomic number is 15. So if I go through and do the math, I can see, okay, I started with 32, but I only have 31 now. So whatever's missing has a mass number of 1. Started with 15, ending with 15. So I don't need any charge. What kind of particle has a mass but no charge? A neutron. So the way that we depict neutron is like that. Mass of 1, charge of 0, and for neutron. That really doesn't give us a type of decay. I have to go for process of elimination here. Nuclei don't just spontaneously start breaking apart and giving up protons or neutrons or even electrons. So the only logical answer here is I need something that doesn't have an atomic number at all, but does represent a decay of some kind. The only one that fits that description is the gamma radiation. And let me explain why that happens. Remember, gamma is the highest form of radiation. It's the most energetic light that we have. And so if a nucleus emits this kind of radiation, one of two things is happening. Either we've got it in an extremely excited state, and that gamma radiation is just what it needs to shake off that extra energy, or we have something like this happens where the gamma ray gets emitted, and as it is just dropping all of that energy out, something shakes loose. A proton, a neutron, something along those lines, pops off the nucleus as part of this spontaneous large emission of energy. So that's what we look for in gamma radiation. We usually look for a minor change in the nucleus coupled with a large export of energy. And that's what makes it different than the other types of decay, because the other types of decay, we see a considerable change in the makeup of the nucleus. A neutron turns into a proton. The whole nucleus sheds 4 particles entirely. Something along those lines. Gamma radiation, we rarely see particles with it. If we do, it's something like this. A neutron shakes loose or a proton shakes loose. But aside from that, it's all energy. And that's one of the reasons why it is so damaging, is because it is all energy. There's no particle component to kind of slow it down. This energy just passes right through you. Particles, they're subject to size. And that size is going to limit their effectiveness in terms of being able to interact with other things and cause radioactive kinds of reactions to occur in your skin or in different parts of your body. All right, are there other things that we want to talk about? All right, so a question like this then, this is from exam 1. You have a placard for DEF, diesel exhaust fuel. How do you make sense of that? So what you have to remember is that the NFPA placard has a ranking system 0 to 4. 4 being the most dangerous, 0 being no danger at all. And then you have to also concern yourself with the extra pieces that might be in that white portion of the placard. So the first thing that you should remember is that the 4 zones, the 4 colors do have representation. They do mean something. So the blue area refers to health hazards. Now that we've had a better understanding of toxicity, we can get a little bit better understanding of what that actually means. 0 means it's completely non-toxic. 4 means that it's not only toxic, it's probably got a pretty robust LD50 or LC50. Doesn't take a whole lot of, it's probably an inhaled hazard instead of ingested, just because we know that inhalation is the fastest mode of entry. On the flammability scale, Again, 0 to 4. 0 meaning the substance is not flammable at all. 4 meaning that it is extremely flammable. And if you remember from our flammability unit, we're talking mainly here about two ideas: flash points and boiling point. So how quickly, how easily does the substance volatilize and turn into a gas? How quickly and easily does that gas burn? For reactivity, what we're really getting into here is explosive potential. 0 means it's completely stable. 4 means it is a likely explosive or an oxidizer that is capable of creating an explosive. And then the white area here contains other information about potential hazards. Things like the W slash, indicating that it's a water reactive substance, so don't bring water anywhere near it. Or trefoil, indicating that it is a radioactive substance. Words like oxy or core, indicating an oxidizer or a corrosive. An acid or a base. Acid or for alkaline, meaning basic. So that's the kind of stuff that you have to be looking for. So if you go to the exam itself, right here, it tells you, okay, there are 4 hazards associated with this. You should be able to look at it and go, okay, first and foremost, I noticed that 4 there in flammability. We're talking about a substance that at room temperature, it is likely to catch on fire if we have the right stimulus available. Because remember, the lowest tier of flammability in terms of easiness to catch on fire means that it flashes at or below room temperature, and it boils at temperatures less than 100 degrees Fahrenheit. We're talking about really volatile stuff, really flammable stuff. If you get a question like this, that's exactly what you say. 4 means extremely flammable. It's dangerous at room temperature. Two, health hazard, means that we're talking about something that is moderately toxic. Now, the NFPA placard doesn't give us any more information than that, really. In the notes I gave you, moderately toxic is really as much as we said. That's really all that we can get into without looking at the SDS. If you look at the SDS, which is another thing we talked about in chapter 1, that safety data sheet tells you, okay, here are the modes of entry, here are the toxicity limits, here is what OSHA has to say on the matter, You can look up those specific things about it. Again, the whole point of a placard isn't to give you all of the information all at once, but to alert you to the fact that there might be dangers associated with the substance. And if there is concern about those dangers, to refer to the safety data sheet to get the correct information. With a health hazard of 1, we're talking about something that is unstable and likely water reactive, which directly correlates to that W slash. W slash telling us don't bring it in the presence of water. Why shouldn't we bring it in the presence of water? Well, reactivity says that it will be unstable when heated. We also know that maybe it's going to react with the water based on that W slash. Maybe it doesn't create an explosive or a flammable substance. But remember, water reactive materials don't have to do that. They can be things that create corrosives when they come into contact with water, or create toxic gases when they come into contact with water. They just have to have some kind of reactivity. But that's how you approach a problem like this, is you look at it, you look at each of the four squares and you say, okay, what is this trying to tell me? Okay, diesel exhaust fuel is really flammable, which, I mean, that's kind of an understatement. It's exhaust fuel, it's diesel. You expect it to be flammable. But we know that based upon its values, we're talking about something that's really flammable, really volatile, dangerous even at room temperature. Got to be really careful about how we store it. That is first and foremost the primary hazard with diesel exhaust fuel. Now, on the other side, yeah, the next most hazardous piece there is its toxicity. Probably don't want to inhale the vapors, definitely don't want to drink it. And then it's got reactivity issues with water and stability issues with heat. And that's really all you'd have to say. All right, we got time for maybe one more question. Okay. Like drawing? Okay. All right, so let's go back to the practice test. Okay, let's not go back to the practice test. All right, so let's look at a common compound that would do that kind of thing. Let's look at COCl2. So for carbonyl chloride, COCl2, the thing that we would have to do first is we've got to draw all of the elements and put all of their dots around them to see how they're going to link up. So carbon is element number 6, but it's in group 4A. It's going to have 4 valence electrons. So 1, 2, 3, 4. Oxygen is in group 16. Group 6A, it's going to have 6 valence electrons. 1, 2, 3, 4, 5, 6. Chlorine, there are 2 of them. Each of them are in group 17. Group 7A, they have 7 valence electrons each. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now, with the way that I taught you how to draw these structures, if you've done this part correctly, then you really only have to do 2 things. One of those things is you have to identify what atom goes in the middle. The one that goes in the middle is the one that has the most unpaired dots on it. Now, I've already kind of set that up by the way that I've drawn these out. Usually a pretty good clue is that that element that's listed first is usually the one in the middle. But even without that information, I can look at each of these and say, okay, this one had 2 unpaired electrons. This one has 4 unpaired. This one has 1 unpaired. This one has 1 unpaired also. If I can do that, then the next thing to do is literally to play connect the dots. I just need to connect unpaired dots with each other, going out from the center to the others. And so I can see, okay, carbon has an unpaired dot, chlorine has an unpaired dot. Let's connect those. Let's do the same over here. And then to get the double bond, I recognize that carbon has two unpaired dots and oxygen has two unpaired dots. And if I pair them up together, that's where my double bond's going to come from. Every pair of dots that we link up is a bond. So if I put that carbon in the middle and I put the single bonds to each chlorine on the side, the chlorines still have their 6 paired up dots around them. The oxygen, because it's got 2 sets of lines, because it's got 2 sets of dots connecting, that's where my double bond comes from. I have 4 dots that are not connected. There's where my double bond goes. So counting it up that way, again, we're trying to follow the octet rule. So every single atom should have 8 electrons around it in total. Well, if I look at the chlorine, it's got 6 dots, so that's 6 electrons, plus the bond, which is 2 more. 6 plus 8 gives me 8. Same thing for this chlorine here. For the oxygen, it's got 4 dots, plus 2 more bonds. Each bond is 2, so that's 4 in total. 4 plus 4 is equal to 8. And for the carbon in the middle, it's got no dots around it, but 1, 2, 3, 4 bonds. 4 times 2, there's your 8 electrons there. So when it comes to knowing when to do a double bond, it has everything to do with the needs of the atoms there. So you cannot make a double bond if you have something like chlorine here that only has 1 unpaired dot. Or something like hydrogen, which only has 1 dot to begin with. Double bonding is going to come in for the substances like the carbon group, the nitrogen group, the oxygen group, where they've got at least 2 unpaired electrons in there. And the needs of the atom require more than 1 set of dots to be linked up. All right, any last questions? All right, so I have office hours today at 11 and at 1. And I'll be around a good chunk of Tuesday as well before the exam. So if you need anything from me, feel free to reach out. Otherwise, I will see you Wednesday morning at 8 o'clock for our last hurrah. Have a good day.